Hello again, Math 1 students. This is section 11.4, Congruence and Transformations. So today we're going to identify congruent figures. We're going to describe what a congruence transformation is. It's another word for rigid motion. And then we're going to learn a couple theorems about congruence transformations. So first we'll look at congruent figures. Two geometric figures are congruent figures if and only if there is a rigid motion or a composition of rigid motions that maps one of the figures onto the other. Here's the key takeaway. Congruent figures have the same size and the same shape. Not congruent figures do not have the same size or the same shape. In other words, with congruent figures, you could flip it, rotate it, spin it, move it, and at some point, the two shapes will overlap each other perfectly. If they're not congruent, no matter how you rotate or move the figures will not perfectly overlap. So you can identify congruent figures in the coordinate plane by identifying the rigid motion or composition of rigid motions that maps one of the figures onto the other. So remember, a composition is two or more transformations. So you could have a translation, a reflection, a rotation, or some combination of those three. So recall from the translation postulate, the reflection postulate, the rotation postulate, and the composition theorem that translations, reflections, rotations, and compositions of these transformations are all rigid motions. They don't change the size or shape of the figure. They just move them around, spin them around, and reflect them. Example 1a, identify any congruent figures in the coordinate plane. Explain. Now in this case, explain means to describe any rigid motion. So which shapes are the same size and shape? So square ABCD is a translation of square NPQR. Notice that ABCD is 2 units to the right and 6 units above square NPQR. So in this case, we would say square ABCD is congruent. So there's your congruency symbol, is congruent to square NPQR. We also have triangle IHJ and triangle STU, and triangle STU is a 180-degree rotation of triangle HIJ. So if you rotate it, turn your paper upside down, you'll notice the coordinates are exactly the same. So because it's a rotation, rotations are rigid motions, we would say triangle HIJ is congruent to triangle STU. Finally, we have triangles KLM and EFG. Notice that KLM is a reflection of triangle EFG in the x-axis. So basically, you're reflecting it so that it's the same distance away from the x-axis. So because a reflection, again, is a rigid motion, triangles EFG and KLM are congruent. Example 1b, identify any congruent figures in the coordinate plane. So again, we're going to look for rigid motions. So let's start with the rectangle NPQR. It's a translation of rectangle GHIJ. In fact, NPQR is 6 units down. So we have a translation. You're basically moving the rectangle down 6 units to get the new shape. They're congruent. So rectangle JHIJ is congruent to rectangle NPQR. Next, we have two triangles. We have triangle STU. It is a reflection of triangle KLM in the y-axis. And notice that both these triangles are equidistant from the y-axis, which is there. So triangle KLM is congruent to triangle STU. Remember, reflections are rigid motions. Shapes are still congruent. Finally, we have triangle ABC and triangle DEF. If you notice, triangle ABC is a 90-degree rotation about the origin of triangle ABC. If you were to rotate your paper, you would see that the points match up. So triangle ABC is congruent to triangle DEF. Again, rotation is a rigid motion. Next, we have congruence transformations. Another name for rigid motion or a combination of rigid motions is a congruence transformation because the pre-image, which is the before image, and the image, which is the after image, are congruent. The terms rigid motion and congruence transformation are interchangeable. They mean the same thing. Example 2a, describe a congruence transformation that maps parallelogram ABCD to parallelogram EFGH. Now notice that parallelogram EFGH, first of all, is a mirror image of ABCD. Notice the pointy part of the parallelogram, the blue one, is at the bottom left, but it's for the green one, it's at the bottom right. So if you were reflected in the y-axis, then you would have the same orientation as the one on the bottom. So you can first do a reflection in the y-axis, and then you could do a translation. So you reflect the original shape in the y-axis, so you get A prime, B prime, and so on, and then you would take that red parallelogram and translate it 4 units down. So that is one way to handle the transformation. Now you could also have reflected in the x-axis and then shifted it to the left. You would end up with the same result. So there's more than one answer to some of these. 2b, describe a congruence transformation that maps ABCD to PQRS. Now if you look at it, it looks like a rotation, and it is. So let's take a look at one of the points. You can do this by rotating your paper. So A is at 1, -3, while P, the companion point of point A, is at 3, 1. Now notice the rule is A comma B becomes -B comma A. You switch the coordinates and then you flip the sign of the x coordinate. But basically what's happening is you have a 90-degree rotation of quadrilateral ABCD in the origin, about the origin, to get the new green shape. Next, we have the reflection and parallel lines theorem. If lines K and M are parallel, then a reflection in line K followed by a reflection in line M is the same as a translation. So you have segment AB reflected twice. You end up with this green segment that is parallel to the old segment, such that you could have just moved the first segment, the blue segment, over, and you would end up with the green segment. So 2 reflections over parallel lines is the same as a translation. Here's the confirmation. Notice how the original segment AB is basically just the green one, but shifted over to the right. Another rule is that if A double prime is the image of A, then A double prime is perpendicular to K. So this is A double prime. It's perpendicular to K, and it's also perpendicular to line M, which means it's going to be parallel to if you draw B double prime there. A double prime is also twice as long as the distance between the 2 parallel lines. So if I could erase all this, that means the distance here from A to A double prime is twice the distance in between the parallel lines. So it's basically double the distance between the 2 parallel lines. Example 3, the diagram, a reflection line K maps GH to D prime H prime, and then a reflection line M maps G prime H prime to G double prime H double prime. You're told HB is 9 and DH double prime is 4. So those are the numbers on the shape. Name any segments congruent to first GH. Now GH is the original segment, so both the transformation segments, the 2 reflections, those end segments are going to be the same as GH. So GH is congruent to both G prime H prime and G double prime H double prime. When you have a reflection, you end up with congruent shapes. Next we have HB. HB is going to be congruent to H prime B. So this is also going to be 9 right there. Finally, we have GA, which is congruent to G prime A prime. So this is going to be congruent to this. Now the question arises, does AC equal BD? And the answer is yes, because G double prime and H double prime, which are these 2 long segments, are both perpendicular to lines K and M, which means that 2 lines that are perpendicular to the same line, they have to be parallel to each other. If that's the case, then AC, BD are opposite sides of a rectangle, and then AC is equal to BD. So basically you have 2 pairs of sides that are parallel, 4 right angles, so you got a rectangle. Opposite sides of a rectangle are congruent. 3C, what is the length of G double prime? So how long is this whole thing here? And remember, it is twice the length of the distance in between the 2 lines. So we said that BH prime was 9. We know this is 4, so this whole thing is 13, which means the length of the entire segment has got to be 2 times 13, or 26 units. Last but not least, we have reflections in intersecting lines theorem. If K and M are 2 lines that intersect at point P, first a reflection of segment AB over line K, followed by another reflection over line M, is the same as a rotation about point P. Okay, it's basically like spinning it around the point where the two lines intersect. In other words, two reflections over a pair of intersecting lines are the same as a rotation at where the lines intersect. Now the angle of rotation is 2x degrees, where x degrees is the measure of the acute angle or right angle formed by lines K and M. So x degrees is the angle here. It's basically where KPM is, or that angle, and now the angle of rotation is double that. Example 4a, in the diagram, the figure is reflected in line K and then reflected in line M. Describe a single transformation that maps F to F double prime. So what you have here is two reflections over lines that intersect. And that's like a rotation around the point where they intersect. So going from F to F prime, two reflections is the same as a rotation around point P. Now the angle of rotation is 2 times the single angle of rotation. In other words, the angle of rotation is double what the angle is between lines K and M. And so the angle of rotation is 140 degrees. So what we would call this is a single rotation of 140 degrees about point P. So this is 140 degrees to go around. Finally, 4b, in the diagram, the figure is reflected in line K and then reflected again in line M. Describe a single transformation that goes from F to F prime. So the question is, how many degrees is this? It's 2 times the measure of the angle in between. So it's 2 times 58, or 116 degrees. It is a 116 degree rotation around point P. That's it for section 11.4. If you have any questions, feel free to hit me up with an email or a post in the Google Classroom.